Good day, everyone. I'm Jairo Madrona. Today, I will be presenting an overview on how we can deploy machine learning model on FPGA. This topic links AI and hardware design, offering opportunities for real-time and low latency applications. And this will be the topic outline. So first, we will discuss an overview of FPGA. This is for those who are not yet familiar with FPGA structure and the process on how we can deploy machine learning model on FPGA. Okay, first is an overview of FPGA. So we have here an example development board. FPGA is actually this microprocessor here. Okay, this one is the development board. If you want to test the hardware description you implemented on FPGA. So FPGA stands for Field Programmable Gate Array, and this is configurable, right? So you can design your custom digital logic using FPGA. So you are actually building a hardware inside the chip. Okay, so, to define the hardware, we use these HDL's languages. HDL stands for Hardware Description Language. So we can use either Verilog or VHDL. For my topic, I am much more familiar with Verilog, so we'll be using Verilog for the examples. Then I want to highlight this important feature of FPGA, the parallel processing. So this one enables high speed and low latency applications, right? We can use tools like the Intel Quartus Prime. So this is an example IDE workspace of the Intel Quartus Prime. So this one is used for the programming, simulating, and configuring our FPGAs. Or also, we also have other microprocessor, the CPLD, the complex programmable logic device. So we can also use that. So Intel Quartus Prime is an IDE, okay, developed by Altera. So this is where we prepare the FPGA hardware when we integrate later in the machine learning or the machine learning model in FPGA. So this is one of the important tools in integrating both the machine learning model and FPGA. It has a free version, the light version. Other version is, of course, you have to pay. It has additional features you can do with that. To start with, again, this is for those who are not familiar with the capability of FPGA. So we'll start with the half-adder circuit. If you are start learning programming, the first program you are writing is the hello world, right? So this analogous to that. So in hardware description language, this example is like the hello world of let's say the C++ or C programming language. Okay, so we have here an example logic circuit for the half-adder. So we're familiar with this one already. So we have AB inputs and we have two outputs, the sum and the carry, labeled as Cout. So to build the circuit inside the FPGA, so we will describe the circuit. The structure of the language, I will call this for now programming language. So the structure of the language is we have this keyword module, and okay, we will end it with the keyword and module. Okay, this one, the half-adder, is the name of your module. Of course, you can name whatever you want, but to make it more intuitive, so we will name it according to its function. In this case, since we are building half-adder, so we name the module as half-adder. Then we will define the ports. Okay, we have A, B, the sum, and the carry. Okay. So after you have defined the label of your ports, now we will define what type of port it is. either input or output. Obviously, your A and B are inputs, right? So your outputs are sum and the carry out. Okay? After that one, we'll describe now the circuit. So the first we are going to describe is this XOR here. So the sum is the XOR of A and B, and that's the syntax. So the keyword assigned here, okay, of course, assign that the result of A XOR B to the sum. By the way, this type of modeling is data flow modeling. You also have the gate modeling and behavioral modeling, structural modeling. For this example, we are using the data flow modeling. Okay, so I think there's no need to elaborate with this line of code. So that's straightforward. So for the C out, we assign what? Okay, and the and of A and B. Okay, so we assign C out, okay, A and B. And this is now our hardware description language. Okay, so one thing to note here is that all statements are concurrent, meaning these two here execute simultaneously, concurrently. So this is parallel processing. If you are familiar with fundamental programming language like C++, so the notion of execution of line by line execution, if you are in HDL, hardware description language, you throw away that line by line notion, because in hardware description language, these are all concurrent. Okay? And we are not writing actually program here. We are defining the hardware itself. We are building this hardware inside the chip. Okay, so these two, you need to take note of this concept in HDL. Okay, so one other capability of this modular approach is that we can reuse those modules. So suppose we are now building a full adder, and we know full adder is composed of, okay, two half adder, right? We can reuse the module we have just created, the half adder module, into this another module. Okay, we can integrate, or we can instantiate actually those half adder. So we'll create this circuit. Of course, we have again module and end module keyword. So the name of the module is full adder. We'll define the ports. Okay, we have A and B, right? This one. We also have C in. Okay. Then the sum and C out. Okay. So that is our ports. After that one, of course, we will define the ports. So A, B, C in, that is inputs, right? Sum in, C out, the carry out is the output. And we have in between. So let me clear the screen first. Actually, this S1 is the sum of the first half adder, right? This output of the first half adder will be the input of the second half adder. So it's not an input, it's not an output, it's actually a node. So for node, we are using the keyword wire, right? So we have wires. This one is the carry of the first half adder, which will be the input to the OR gate later for the carry out of the overall half adder. So that is C1. That's another node. And we also have node here. The output of the AND will be the input of the OR. So that is your another wire. So we have three nodes in between the two, or yes, three nodes, okay, in between this two half adder, right? Okay, after that one, now we can instantiate this first half adder. Okay, so let's instantiate this one. This half adder here is the half adder we just created before or previously. We instantiate that one, so we name this as HA1. So you can name whatever you want again. So let's say we'll name that, or we can instantiate that as HA1. So this dot here, dot A, dot B, dot sum, dot C out are the ports of your previous half adder, of your module half adder. Okay? This part here, inside the parentheses, are the ports of your full adder module. So A and B. S1, take note, S1 is actually the sum output of your half adder module, right? The same with C1. This is the carry, the first carry from the first half adder. Okay, so that's why we have C1. So all of these inside the parentheses are the ports of this current module full adder. This with that again is the ports, or are the ports of your half adder module. Okay, so this is our first half adder. Then we can also have the second half adder. Okay, we can instantiate. This time we will name that as HA2, half adder 2. And again, we map the ports. Okay, so the same, we have S1, C in. Actually, this is your B, right? So, okay, so we map that B to C in. This is our A, this is our B. Then the sum, this is the final sum. And of course, the C out is the final output. But here we have, okay, so the C2 here is actually the carry out of the half adder. So we have C2. Okay? And that's it. The last one is only the OR. So we OR the this one, the C1. Let me clear this out. So we OR the C1. This is the first carry and the second carry, C2. Okay, so this is the symbol for OR in data flow modeling. So we assign C out as the OR of C1 and C2. Okay, so this is how you describe logic circuit inside the FPGA. Okay, so this modular approach is also similar to the machine learning model approach, wherein we can build module by module. Right? So this is an overview of what you can do in FPGA. And again, the most important thing here is it happens concurrently, not line by line. So take note of that. That's why it is high-speed application with the FPGA. So it's efficient in real time and low latency application. So this half adder instantiation and this assign here happens simultaneously, like concurrently. Okay, that's it for the overview of FPGA. And now let's proceed to how we can deploy machine learning model on FPGA. Okay, first you need to train and convert your model. We have here a simple block diagram. So the first thing is, first you train your model, this one using TensorFlow framework, for example. After you train the model, you convert that into the lightweight format. Okay, so you can use either the TensorFlow Lite or TF Lite Micro. So basically, you have machine learning model, you convert to the Lite format, right? So using this software here. Next one is you set up your FPGA hardware. For example, you will be using Altera, Agilex 5. So you set up that hardware, then you integrate the processor So you can use either USB or ARM, okay, processor. So right here, and all of this peripherals using the IDE, okay, Quartus Prime IDE. So basically, you have your machine learning model, you have your hardware, okay. After that one, so you will install under IDE, the REST-free IDE, okay, for USB and Zipfire OS for ARM. Then you integrate the TF-Lite micro library in Customize to the target platform. So that's include adjusting the timing functions. So we have here the integration of model, your machine learning model, and your hardware. So using this library, okay, the TF-Lite micro library. And after that one, if you notice, you using also our um, Intel Quartus Prime software, so we can deploy that to the physical FPGA or the hardware itself. And that's the next step. So you deploy the model to the FPGA, or you load the model. So using this library, TF-Lite micro library. So if you notice, the flow is this all software. Okay. Then after deployment, so this would be the optimization process. So you test, deployed, you check the accuracy, performance, then you can train it again, okay, based on those data. Okay, so this is more like optimizing your FPGA. And that's it. That's concludes my presentation, and thank you for your attention.